Muito bom dia a todos. Então, sejam todos muito bem-vindos aqui ao nosso laboratório, a nossa série de seminários em energia solar fotovoltaica. Nós temos hoje um convidado, o Dr. Mohamed Reza Agai. Ele é mais conhecido como Reza. Então, o Dr. Reza está aqui conosco, passando 2 semanas como parte de um projeto que é financiado pela Fundação von Humboldt, de intercâmbio entre pesquisadores brasileiros e alemães. A especialidade do Reza é na termografia infravermelha. Ele fez um doutorado nesse assunto no Politécnico de Milano, e ele vai falar para nós um pouquinho hoje sobre o uso dessa técnica, dessa tecnologia para controle de qualidade de usinas fotovoltaicas, desde geração distribuída até usinas de grande porte. O Reza vai fazer a apresentação dele em inglês. Nós estamos transmitindo isso aqui também direto pelo nosso canal YouTube, e vai ficar também gravado no nosso repositório. Ao final da apresentação do Reza, nós vamos abrir então para a plateia fazer perguntas, e eu vou pedir que vocês sempre usem o microfone para que também na gravação fique registrada a pergunta de vocês. Vocês têm que falar em inglês com ele, né? Para então a gente poder fazer isso de uma maneira mais tranquila. Eu passo então a palavra. Reza, the floor is yours, and welcome to our lab and to our seminar series.
Okay. In the name of God, very good morning to all of you. Bonjour. I'm Mohamed Reza Agai from Fraunhofer ISE. I'm a researcher in this institute. And today I'm going to actually talk about some novel methods in control and monitoring in the photovoltaic systems. Thanks to Alexander von Humboldt Foundation, which actually support us for this trip and this visit, which is under one program between the actually Photovoltaica UV and Fraunhofer ISE. Before start, I would like to just a bit introduce myself. My bachelor degree done in electronics engineering in Iran in 2008, and I finished my MBA in Malaysia in 2012, and I graduated in electrical engineering, especially in solar cells. In Unitan in 2013, and after that I joined to Politecnico di Milano, and I finished my PhD in 2016. And as a research fellow visiting, I joined to Fraunhofer ISE in 2015 and finished in 2016. And now I'm research fellow and project manager in Fraunhofer ISE after my graduation. I published more than 22 peer-reviewed conference papers and 1 chapter book, and also 13 referee journals. Before going to the outline of my topics, I would like to talk a bit about the Fraunhofer Gesellschaft or Fraunhofer Society. Actually, Fraunhofer Society is the largest organization for applied research in Europe, and there are 66 institutes under this organization, and around 24,000 staff works in this institute. Fraunhofer ISE is one of its branch, and is the second largest institute, which is located in Freiburg in southwest of Germany. The director of Fraunhofer ISE is Professor Henning and Professor Andreas Beth, and we have around 1,200 staffs there, and the budget for 2016 was 86 million euros, and it's established in 1981. The business area of Fraunhofer is included the silicon photovoltaic, everything related to solar energy, silicon photovoltaic, solar thermal technology, or photovoltaic modules and plant and storage technology. So it is more or less, 7 or 8 departments. Okay, today we are going to talk about the monitoring and operation maintenance, and especially we are going to talk about the methods. As you know, the monitoring is very essential and it is very important for the PV plant in order to keep the performance of the PV system in high level. And accurate monitoring is always complicated and it is always expensive. That's why we need to develop it every day. And the fast detection is very important in order to extend the lifetime of the PV plant. So the automation of this procedure could be very helpful for us. And it is, in the near future, we should actually develop some methods to automate the procedure of the defect detection. Okay, any PV projects include these 5 stages, starting from development to operation. And some people think actually the monitoring services or quality assurance services should be started from operation. But in my point of view and based on the literature, it should be started from beginning at the development in order to reduce the risk at the beginning of the operation of the PV plant. So it is important to actually care about the monitoring and quality assurance from the beginning of the projects, even from development. This is not our topic today, but just I brought this slides in order to show you actually this stage, all this stage should be included the monitoring services. This graph is very interesting. As you can see here, in the first 3 years, even before, during the EPC, most of the failures maybe happen. And at the beginning, in first around 2 years or 3 years, you can detect some failures. So the high risk of the PV plant is here. So based on the previous slide, as I mentioned it to you, if you do the really strong quality assurance, you will see here you can actually extend the lifetime of the PV plant over 25 years. Otherwise, you can see is not really, even less than 20 years. So it is very risky for the owner of PV plant. So it is important at least actually we have a plan for the quality assurance and also for the monitoring. Before I start to talk about the methods, we should to be familiar with some failures. During lifetime of the PV systems or PV plant, our system or modules will be actually exposure to some defects and failures. And this is very normal, but if you have a plan for the monitoring and quality assurance, it can be reduced. The main part of any PV system is modules. So here just I try to bring for you some common defects and failures in order to show you actually the name and to be familiar. I'm sure you are familiar with some of them. Some example is here, as you can see here. This is the SNL trails, which is recently actually detected by some companies, and also it is very new failures. Based on my research, we did a lot of experimental tests to detect the SNL trails phenomena on the PV modules from 2013. Here is, some hotspot in the last lifetime. It's like lifetime. Okay, regarding the some statistical distribution for the general failure area in the PV systems, I brought here 2 different research. One of them from TÜV, as you can see. Actually, they did a lot of experimental tests for 12 gigawatt, and they believe that the modules the defects can be actually exposure in the modules more than 48%, And another experimental test the Sun Edison performed, they declare the inverter is the main actually problems. But in my point of view, the modules, this is more realistic because the module is the main part and is more actually exposure to the external stress. This is the failure modes and the distribution graph for the failure modes in the modules. As you can see, the glass is the major problems actually we can see in the glass, and also the laminate internal and electrical circuit is another problems. And here also another graph is in order to show you actually the optimal failures related to cell or junction box and cable can be actually make problems regarding the some failures. And these two, if I'm not mistaken, both of them actually done by with the 2 million modules after delivery company, and it's started from 2006 to 2010. 40. This is also a specific failures area in the inverter. Here, actually, the Sun Edison declare the control software, actually, based on the ticket they receive from the customer, the control software is 28% and the failures actually can be detected in this side. But other part also have, more or less similar situation. But for example, the cardboard is another problems. They always receive the ticket. This published in these journals by one of the operator in Sun Edison. Okay, in order to detect these defects, we have several methods, but just I brought some of the most important them. We have visual inspection, infrared thermography analysis, PV parameter measurement, signal transmission device, and we have recently some new method by using the UAV application. We will discuss later about this. The first step of any failure detection or defect detection is the visual inspection. So with the sight, you can actually easily have a look to the modules or to the inverter or to cabling and find out actually some problems. But this cannot be actually cannot actually without other methods cannot actually guarantee the defect detection. Some other example I brought here for you. This is bubbling, and this is actually the problem of the cabling, and this is another hotspot problems. This is the last part because the hotspot can be detected at the initiation, but here is really the last part. And the lamination, you can see here, cell breakage, and some moisture inside the modules. Another method is the thermography analysis. The thermography analysis is one non-destructive method, and it can be done without shut down the PV plant. So it is easy to do it, and this method should be done on the operation side. And if the plant is shut down, you cannot not detect anything. For thermography analysis, you need to follow the procedure. And if you want to have a high quality pictures, it is very important to follow the procedure. So it should have a tilted to the object and to the targeted modules, and at least the tilt should be around 40%. And in order to reduce the self-reflection and also some others external objects, maybe make a shading on the modules. So if you want to increase the quality of your pictures, you should follow this procedure. Here you can see some combination of the visual inspection and also the thermography analysis. Both of them can complete each other, and so it is important actually you do both of them at the same time, because sometimes really, some defects you can detect it by the thermography analysis. It's not really defects. Maybe it's, for example, drop of the one bird, or other issue, or one, I don't know, shading. So it is important at the same time you have a look visually and also thermography, with thermography analysis. Another method is actually PV parameters measurements. With PV parameter measurement, as you know, we can actually do some IV curve and or PV curve, power and voltage curve, or fill factor analysis, and also current and voltage in DC side and AC side. Here, just one example, we did one experimental test for the shading in different level. This is the power and voltage curve, and as you can see, in different level of shading, we have a different PV curve. These two graphs is related to the Snell terrace phenomena, which we already detected in one of our modules in Politecnico di Milano. And in that time, some companies actually declare the Snell terrace doesn't have any effect on the efficiency of the modules, but we proved that it's really have an effect on that. And you can see, after the Snell terrace, after 1 year, 2 years, the Snell terrace happened on the modules. We have a reduction of the efficiency of the our PV strings. This graph also is the yield assessment for the Snell terrace strings on the one strings we had, and you can see the reduction in energy also is very clear here. This is the healthy modules, and this 4 is related to 4 modules in one strings, which are already affected by the Snell terrace. Another methods are electroluminescence, which is very interesting, and photoluminescence and UV fluorescence. Actually, if you want to perform the electroluminescence, first you should inject the current. First, you should shut down the system, and you should actually, take out the modules and bring it to lab. Or if you want to do it in the plant, you need, some area, dark area, to perform it. But we have also mobile electroluminescence. You can actually take it to the lab. This is the current sources, and you can inject the current to the modules and try to actually capture the emitted radiation from the modules by the CCD camera, and after that you will have these pictures, and you can see some pictures like this, and you can detect some micro cracks and printed defected and also cell breakage. This is very useful, for such these failures. So I think this method could be very good, but also this is expensive because the camera is very expensive. The UV fluorescence is the same idea, but is different method, because you should first radiate the UV light to the modules, and afterwards you can detect it with the same camera, the emitted actually infrared, and after that you can see such a failures. But this method was not really developed for the modules. It was at the beginning for other stuff in chemical engineering, and for example it was related to polymer, but after that they saw it's very useful for the module, so they use it here. Another method is actually signal transmission device, which is also not used for just for the defect detection in the panels, but it's very useful in order to detect some disconnection part, for example, from the back of panels or in the cabling. So it is very easy. The device is like this. You transmit one current to the modules. After that, you should detect it by some device like this, the current. If you cannot detect it, it means somewhere else, you can find it somewhere else, you have a disconnection. So it's useful to detect, some failures like a bypass diode problems or disconnected modules problems. This is another example is for open circuit and bypass diode problems. Okay. Another method is very useful and recently developed more. It's related to high precision short-term monitoring for the PV system performance. Actually, it is really depends of your device and data acquisition system. How much is have a high performance and high accurate. We developed this system in Fraunhofer ISE. In the one monitoring box, we use the Gantt instrument data acquisition system and connected to the, our rooftop plant, and we try to we try to also capture some data from the meteorological side, and also we had the DC monitoring and AC monitoring here, and at the end of the day we did analysis for that. But for your information, it is around 10 kilohertz per second, so you can detect the signals around 10 kilohertz per second. So as you can see, it's very high, accurate, and also it's very expensive. This is more detail of my design. We did it in the one box for our engineering because they went to the PV plant and they needed to have a, in very carryable box in order to do some tests and do some calibration on the site. And we have some data logger here, and this is the two data acquisition systems, and we connected like this in our box for our engineer in Fraunhofer ISE. We will talk about this later also. Some data anomalies I brought here. This is between around 11:30 at morning to 40:30. So it's just to show you actually it could be very high accurate, but I think this just is 2 kilohertz per second. We detect some defects, but the defects was really the failures was really related to noisy problems. But afterwards we did another methods for the analysis the PV systems in order to make sure that these defects is really related to PV systems or external sources. Okay, another interesting method is using UAV or UAS, Unmanned Aerial System or vehicle. Actually, UAS application is not just for the PV plant, it is for different mission like military services or even monitoring for the other part. But if you want to have a very good UAV for the PV plant, it is very necessary to have it in, for example, low altitude, and the range should be more or less short, and the size should be mini, and weight should be light in order to have a good performance in the plant. During my PhD, I tried to develop one system The systems was just, I mean, part of my system was actually using UAV with 2 different sensors at the same time. This UAV developed one company, the name of company is Nimbus, and it is really developed for the PV plant inspection. And at the same time, also as I talk about this monitoring box, we connected this monitoring box to the plant. And at the same time, we try to automate all procedure of the failure and defect detection on the PV plant, and afterwards all data stored here in the database, and based on the previous methods, previous monitoring data, we try to develop one software in order to analyze the image which is captured by the UAV, and also the signals which is captured by data acquisition systems. And afterwards, we try to also develop another software to automate, and also for the final decision based on the previous data, we develop it. So this is one really, I mean, comprehensive and innovative systems which can cover, I mean, the image side from the UAV and also the signal side from the data acquisition system, in order at the same time you have all data together in order to analyze them. This is another schematic of my systems, but include the SCADA, and is the same, but is also connected to SCADA, which is more or less same idea. But I published it in the IEEE Photovoltaic journals in 2016. With this system, we did a lot of experimental tests in north of Italy, and more or less around 4 megawatts. And we capture many faults in that plant, and this is just some example I brought for you. The bypass diode problem, hotspot, but this hotspot is not really hotspot because it's related to the, I mean, drop of bread. So as I told you before, it's important you do it together. And also this is also happened because of this shading. This hotspot really is hotspot, and it's because of this shading you can see here. Yeah, there are some other examples here. You can see the disconnected modules, which is captured by these systems. Another important issue is when you are using the UAV, it is important to have some plan for in order to reduce the mistake and errors. So you can see here in the left side, the UAV when flight, there are many external issues may affect on your pictures and images, so you should try to reduce it. So one of them could be the self-shading or self-reflection, and also some objects may make actually shading on your targeted modules, and so it is important to actually reduce this part, and before fly you think about that. Based on our experimental tests, we understood the best angle. If you want to have a high quality pictures, the best angle is perpendicular, and it should be exactly, on the targeted modules, and it is very important also. And another actually experimental test we did, and we developed one equation for that, and we received the award for these equations and these papers. We try to do some analysis in order to find out what is the correlation between the altitude and also the resolution of the sensor and the potential of the specific detection of the specific failures. So here H is the height, A is the altitude, E is elevation, and GD is ground distance. You can see here ground distance, and H is the height, and also here you can see the photo distance, and this F is the focal plane from the sensors. So according to our experimental test, we found out, for example, the snail trace can be detected in 5 meters, and the dirty module can be detected in, for example, 50 meters, but it depends exactly about the shape of the, dirty, and also the size. But in that time, we understood this, the normal way. And also the ground resolution can be detected for that is between 8 and 10 pixels per centimeters. Okay, I'm sure you are familiar with this table, but just I bring it for next slide. As you know, all actually failures in thermography analysis has the specific patterns. So based on these patterns, I try to develop one software in MATLAB in order to detect these patterns. And based on the average luminance and standard deviation of the luminance distribution of our image, you can detect some part, hot part, and and cold part. And at the end of the day, you can have a percentage of both sides, and you can detect some defects, and automatically you can try to actually detect that defect, specific defects. This is related to that slide, as I show you. This is related to this part also. We put it here also. Okay. I brought two graphs here. This is luminance distribution for one healthy modules, and this is luminance distribution for one defected module. But this defected modules is related to the hot spot, and because of the time, I didn't bring other graphs, but if you want, later on we can discuss about that more, because I develop it for the bypass diode problems, for disconnected modules, for the hot spot, and at the end of the day also I try to use this method to count the modules and defected modules.
Sorry, who is AMD?
Sorry, come again?
AMD, who is?
This is healthy modules is the first, and the defected module is this. Is luminance distribution of the pictures, IR pictures. Okay, just this is the procedure. The visualization of the procedure of the defect detection. This is the disconnected module. This is the bypass diode problem, hot spot, and some other short circuit problems you can detect it here. Another things I did with this system, it was related to image mosaicing. With UAV, you can do some mapping on the PV plan. So it is very important and it is very useful. I published it in one conference paper, the result of this. You can actually have a look on that. But these pictures show you before flight, you should have a plan for your flight. And it is very important in order to reduce the drift and crab. You can see the drift and crab here. And sometimes if you fly with the UAV, it is, you can see actually sometimes it's difficult to manage it, and sometimes it's out of board. And but if you want to have mosaicing or mapping, it is important to follow the planned direction for your flight. And for mosaicing, at least you should have a more or less 30% overlapping if you want to have a good mosaicing. I just want to show you these two graphs. These graphs show you actually the successful mosaicing images. You can see is more or less after capture many images. We just try to combine it by some methods, Harrison method in the image digital image technique, and this is also some other pictures we already captured by the IR sensors, but as you can see, the flight was not really online, and that's why the final image mosaicing was not really successful. Okay, the summary. I hope, yeah, exactly, I'm on the time. Okay, today we discuss about the operation and maintenance and how much is important and what we should do about that, and also some recent development in this field in order to failure detection, and how we can have an accurate inspection method for the defect detection, failure detection. And also we talk about some methods, especially about the traditional method, about using IR and EL, and also we talk about the combination of all of them in one system, as I introduced to you, in order to do all of this procedure at the same time and make it automation, and at the same time we do the analysis. Thank you so much for your attention, and if you have any question, it's my pleasure to answer.
Thank you, Reza, for your overview of all these new techniques, some of them not that new, and on concentrating on the topic that has brought you here. So we now can take questions from our audience. Come on, the PhD students should have a smart question each, at least. Okay.
So if you compare the data you collect with the drone and you compare it with the monitored data you collect from the ground station, the one that kind of compares the power that is generated with the power that should be generated, which one is the better or a more accurate method to make sure that your power plant is actually reaching the power it should be?
Actually, by using drones is more faster, and this is one advantage of the using drones. And at the same time, if you have a really high qualified sensor, it is easier to detect the defects, and it's very faster, and at the 1 hour view you can actually detect many defects. But as you know, the traditional methods by using, for example, IR camera or visual camera, it takes always time, and normally it's not really cost efficient, because you should put many people there and they work for you, and it takes always time. And in sometimes I forgot to say something in my slides. Sometimes if you just put it in the human side, based on the human experience, they can actually mention it in the report something. But if you just put in the software side, the software never actually have any problems, because the software actually the software experience is based on the previous methods. And so for example, with the deep learning and machine learning, you can actually have a better overview for the defect detection.
I have a question for you. You have been here with us for a whole week now, and you've seen what we are doing here at the lab, and you went also to our experimental power plant, the 3 megawatt power plant in Tubarão. And you also know that by the end of this year, Brazil will have its first gigawatt of mostly large-scale PV power plants. Based on what you've seen over the last few days, what do you reckon will be the potential of all these techniques that you showed here to detect failures, and what we need to be prepared for?
Me and Aline and Edward, we try to perform this by using that drones, but that drones is not really developed for the actually PV plant monitoring. But anyway, we try to perform this for the IR sensors. So because I didn't do it in that time for the IR, but just I focusing on the visual. So we did the same experimental tests to detect some defects, but not defects related to visual side, the defects related to IR side, and we more or less did, but we still need time to analyze this. Another things I talked with the guy, I think my suggestion is try to develop one new UAV, especially for the PV plant, because this UAV is not really, modified for the plant. So my idea is if you can actually try to have a collaboration with one company, at the same we did in the one company in north of Italy, and try to give them, your data, and they should produce new one for you. I think this is very useful.
Yeah, this is just a commercial drone that we're using. Mm-hmm.
Hi, Haza. Also about your visit here, you did these experiments in Germany and Italy, right?
Yeah.
What do you see, like, is it here, there that you do it already, is natural? Here is more, it's easier for us to do it, right? Because we have better conditions. What do you see the difference? Because there it must be hard because you don't have radiations, good irradiations every day as us. What do you see? What is the comparison?
Just the differences was regarding the defects. I think the defects and failures, because we have a specific failures there. For example, in some area in near to Middle East, because we have several experimental tests in different countries, we have soiling problems. But here in Germany, we don't have problems like this. And there is no any difference really, because if you want just talk about the images, there is no any problems because we are just going to find the defects and failures. But if you are talking about the signals, if you want to just talk about the signals with the data acquisition system, of course, this is the difference from here, because here there are better radiation, and in most of the time in Germany we have a cloudy problem and raining, so it's difficult to have good data. So there is no any other differences in my point of view.
Okay. In what way the IR image can add to, let's say, the diagnosis of the failure, like on the electrical side? Is there a correlation between the delta T and the electrical outcome? And for warranty issues, in what way it can contribute to warranty issues?
I didn't get your question. Could you please repeat it?
Well, my question is related to the fact that when you have the IR image, like you detected a hotspot, how can it add to a better understanding of the diagnosis, like on the electrical side? Is there a correlation between the delta T and which can be drawn on the electrical side, or how can it add to a better understanding of that?
Normally, in the electrical side, when we do some tests, we just not rely on this performance test. We go to the plant and we do more tests, and we try to actually understand better about is it external factor or internal factor for the defects and failures on the PV plant, but sometimes is related to the calibration of the sensors. So we should do some tests in order to make sure that this is not related to calibration of the sensors, because, for example, our sensors always calibrated, and our engineer, when they go to the site, they always use our sensors, and we don't care about their sensors. We just try to find out actually the calibration is correct or not, but after that we can do the other test after making sure the calibration is correct. So normally it's like this. I hope I could answer your question.
Yes, another part is whether you were able to draw recommendations of the temperature level to warranty issues, to the necessity to change the module, or to go to the manufacturing?
Yeah, normally after we see the, like these problems you mentioned about the hot spot or sub-hot point, we take out it and bring it in our lab. We have a lab in Fraunhofer, and we do some other tests, and if it's really related to the, actually the external issue, and is not related to the, the mistake of the person in charge there, so it could be actually included the warranty issue.
Okay, but like concrete correlations, like 20 degrees above the temperature of a healthy cell, okay, the module needs to be changed immediately.
Any panel has a, different regulation and terms and conditions for warranty. But in my point of view, the 20 centigrade is not really the case. But for example, we did in our experimental tests in that plant. You remember we saw some of the hot points, which is very, very hot, and it's around 100 degrees. And we saw other parts. It was not really hot, but it was more or less just it was not homogeneous. So in my point of view, in the one panels is not really the case. If just the 20% is the difference the temperature, you can actually detect it by the IR. But anyway, it is initial problems, so you should have a solution for that. So you should think. So that's why we try to do some detection before any action.
Let me just complement. I think the question also relates to claims, and some financial institutions who are financing these power plants, they want to know what is the delta T that is that will lead to a warranty claim. So from what stage do you say, okay, this module will need to be replaced because otherwise we will not, this is a claim, a claim of warranty?
In our department, we have a collaboration with Allianz and VDE, FADE. And before starting, any projects, if we have a report for quality assurance services, we just report the current status of the PV plant. Afterwards, based on this report, they have data. And based on this data, after, for example, 1 year, 2 years, 3 years, it depends of the contract. This delta T or any kind of indication, it's already defined before start the projects or before the commissioning. Afterwards, we see anything, it's again come back to this report, and after that we can actually talk about that. But it defined before, so
it's a contractual issue.
Yeah,
then.
Yeah, exactly. It's not really. Depends on the current situation. You should first have the status of the plant and under operation. And after that, if everything is okay, the Allianz will, issue the certificate, and based on this certificate, this is guarantee for the plant. And if we see later, it really depends. It depends of is it, really related to human side or external factors. And afterwards, we can do the same.
Hi, Hazza. My question is also about the contractual issues. I'm using Deutsche Bank as my example here. Deutsche Bank is stating that besides the infrared thermography, to have a full picture about the healthiness of the PV plant, they also are asking electroluminescence analysis of a few models. Do you think that this is feasible and practical for a large PV plant, or one step ahead? You think that we are close to have a solution of aerial electroluminescence analysis in large PV plants? And do you think that this is, let's say, good and have a full picture about the healthiness, or just the infrared is enough?
Normally in our department we do the EL just for those modules we know, this module has some problems. And for example, for 110 megawatts, we do more or less, randomly for 40 modules. for 40 modules for 10 megawatts. So it's not really necessary, but you can do it randomly, the check for the, I mean, more or less, I don't know, 3 megawatt is here, right? Okay, so 3 megawatt is maybe less than 15. So this is the normal procedure we have in ISE. And sometimes we do the same test here in procurement for the owners and also for the bank or, I mean, other people. But after operation, after first year, we can do, I mean, some other tests for EL, but most of the time our engineers do the IR because it's more easier and can be done. But for your information, actually recently, I mean, some new camera, CCD camera developed, and you can do it, I mean, in the daylight, the EL. So it's more easier, but it's very expensive. So in my point of view, I mean, it's not really cost efficient.
Heza, can we back to slide, I think it's 37.
Who can help me? I cannot see here. Okay. 37?
Slide 37, I think. Yeah, I think it's this one. Yeah.
Okay.
So, in the percentage over defected models, you have 25% hotspot. And do you know the main causes of these hotspots? Because when you are saying cracks in the cells, you are mentioning visual cracks, cracks that you can see. This is not micro cracks.
No, because we didn't do any EL.
Oh, I see. Okay, and do you know the causes of these the main causes of these 25% hotspots?
Most of them was related to shading.
Shading.
Yeah,
I see.
Shading, and some of them was related to the, I mean, non-homogeneous cleaning, because in part of, I mean, modules you have a one shading, but the shading is related to the, for example, the rough of the bread, or I mean, one leaf, or something like this, or even soil problems. So it is not homogeneous. That's why actually make a hotspot. But this distribution, as you can see, and this data is just for 4 megawatt in north of Italy.
I see. And I think 2 slides forward, you have one image. Yeah, this one.
This one?
Okay.
Okay.
Yeah. So you have a drone over a thin film model, yeah? So it's
This
the
one
image
or
in the middle. Yeah, exactly this one.
Okay, perfect.
So, and also doing a connection with your algorithm that you develop in your PhD. So basically that algorithm is based for crystalline models. I mean about the pattern of the failures, yeah? But you think
but
that...
this is multi-junction modules here. Yeah.
Ah, okay, but... Okay, but let me put bringing my question to the thin film models. Do you think that also your algorithm could be used in thin film models, or a little bit more? You think that infrared, aerial infrared thermography, it's also suitable for thin film models? Yeah,
but it was not really fit for, I mean, thin film module. But I detected, for example, here we had some white spot, and it was detected by the IR camera, and we could actually analyze it, but that program I developed it in MATLAB. So it works, yeah, but I didn't actually, I mean, focusing about the thin film, just I focusing about the crystalline, yeah.
Okay, and my last one. Here in the audience also we have some metallic structure manufacturers, yeah? And a few manufacturers in the market, they are claiming also that the metallic structure could lead to a hotspot in the in the frame of the model due to the stress of dilatation. Also, this is something that you are seeing in your inspections, or you saw already?
In our experimental tests, I didn't find a lot, but I found it. But you are right, in some places, yeah, you can find it. I brought these pictures, but this picture is not related to me, but just for your information, if I'm not mistaken, you are talking about this, right? More or less, such as these problems, or such as these problems, right?
I mean, really in the frame, let's say in the connection between the model and the mounting structure. I mean,
you know, most of the problems for related to that. I mean, the frame is really it depends of the the installer. So just sometimes when I went to the some PV plant, I understood they actually keep it very strong, and after some months or some days it's broken. Maybe just with the single mechanical load, actually you will see the it's broken. Even maybe the glass broken because of this. So that's why also here declare in the EPC side, most of the failures happen in EPC side. So it is important, you work with the high qualified EPC companies. So you're right, yeah. But I didn't see too much, but yeah, I saw it.
Any further questions?
Right now, you're using the UVs to identify modules with problems, right? And how could you use it to do preventive maintenance, like identifying a module and monitoring it before it is causing a problem?
Your question is, I couldn't understand.
How could you use the UAV
okay,
to do preventive maintenance of the modules?
Okay, you mean prevent any defects and failures? Yeah, actually we do, using the UAV exactly for that part, because if you have the fast detection, procedure, for example, UAV is one of that. If you have a fast procedure for that, for the monitoring the plant, it's easy to detect very fast. And for that defects and failures you saw, you will have a fast solution. And that's why the UAV can help us to detect the defects, because we are not talking about the 10 megawatt. In some plant, for example in China, is around gigawatt. So you have a big plant and you cannot actually send 100% people there and work on that. So it is important, at least each year have some data. You can rely on that, and after that, based on this data, you can have fast action. So this is the application of UAV for using monitoring services for the PV plant.
Mais uma pergunta aqui.
You were talking about the overlap that should be around 30%, right? The
Overlapping
pictures,
for
yes,
the mosaic.
for the pictures. And I would like to know if you are using any special type of software, like Pix4D or whatever.
There are many software for that, really. But if you want to, develop, you are talking about mosaicing, right? Okay.
Yeah, the mosaic.
This was my experience. There are many software, even you can do it in the Photoshop, but it's not really precise, because I check some other software for that, but it's not really precise. But for mosaicing, based on my experience, the 30% should be okay, more or less. But it really depends on this, because even you just follow the 30%, even you didn't follow this structure, it's really difficult to have a successful mosaicing. But this is very good for the large scale PV
analysis. Yeah. Thank you.
Okay, so I think everybody is happy. Thank you again for this very good presentation. We're glad to have you here and hope to have you back soon. Thank you.
Thank you so much for everyone. Thank you for
Henrique.
coming.
Okay, thank you. If we are talking about pictures in the field, how frequent do you think it's feasible to do research? And I mean,